Imagine you're tasked to design an architecture for a new innovative product at your company. And you've gathered all the necessary requirements such as scalability, reliability, performance, cost. And at that stage, you might ask yourself, what would be the optimal compute platform to choose? How many TPS do I want to handle? Do I have sudden traffic spikes? And can my requirements be fulfilled via containers with an orchestrator, or can I use serverless functions? So today, we want to equip you with a toolbox to be able to make this decision on your own while navigating the trade-offs. And as a quick spoiler alert, this will not be a binary decision. So let me all welcome you to DOP304 containers or serverless functions. When to choose what. My name is Maximilian Schellhorn. I'm a senior solutions architect with AWS, and this is my colleague Emily Shea, worldwide lead application integration, who will cover the second half of the talk. So we will start off a bit with the fundamentals. So what makes container and serverless functions unique, understand their scaling behavior, their core integral parts, and then we will evaluate them from a cost perspective, from a management perspective, operational perspective, and close it off with a couple of real-world examples so you see when to use what in action. So let's look into our two candidates for today, containers or serverless functions. And if we look at containers, I think over the last couple of years, we have seen a big evolution in that area, right? In comparison to traditional virtual machines, containers are able to share the underlying operating system kernel and are therefore much more efficient and also much more portable than virtual machines. So you can put much more containers on a single machine, and they rely on Linux concepts for isolation, such as C groups and namespaces. And if we look into the anatomy of a traditional container, we usually see a couple of layers, right? So we have our base image, which is our operating system that we want to leverage. We have a certain runtime, depending on the application programming language that we're choosing, like a Java with a JVM, JDK, and so on and so forth. And then we have our application. And if it's a traditional web application, we might have an embedded HTTP server in there or some kind of framework that we're using. Now, when we take that image and we run that afterwards, we have a running container, right, with all the parts that we've just explained. But obviously, a container needs to run somewhere, so we have some form of underlying compute node where that container can be run. And the only thing that we need to have on that compute node is the container runtime. And the container runtime is that kind of piece of the puzzle that makes that container portable, because I only need to have the container runtime on the specific compute nodes, be it local, in the cloud, or on-prem, and then I can port that container to there. Which allows us also to have very efficient migrations, right? Not a lot of things would change in that context. Now, running a single container is relatively easy, right? If I just do Docker run, it's quite simple to get it up and running, but usually I want to have multiple instances of that container running, so I need some form of container orchestration that ensures that I have a given set of containers running at a given point in time. And usually, the container itself also does not live in isolation. So usually, it communicates with other components in the network. I can expose the container on certain ports. I can really define on port 80, 80, 90, whatever. I'm completely free to expose functionality in the network and call whatever I want that I can reach in the same network. We have additional components like a load balancer that is there to route the traffic to multiple container instances. And I think this has been production-proof, and probably most of you are familiar with that, but I'm reiterating because it also implies certain things that we need to take care of. So first of all, you see all those components, and you usually also need to manage them. You might need to patch them. You need to patch the underlying compute nodes. So there are a couple of moving parts that you have maintenance effort on there. Now, if we look a bit into traditional scaling, and this is not that different from virtual machines in a sense, is that we usually initialize our container once. So this is setting up the HTTP server, for example, exposing certain functionality, and then we have a running container. So usually they are long running and are able to handle multiple requests with the same container instance. There might be a background task that is running, doing some fetching in the back. You might have also a library that fetches something from Kafka or RabbitMQ. So usually containers are long running here in nature. And they usually keep running also after request processing. So even though if you're not doing anything, if you have an HTTP server, it's just sitting there idle 24/7 waiting to accept the request. So we're kind of taking that long-running nature also as given. And from a scaling perspective, we usually see two things, which is first container-based scaling as well as node-based scaling. So container-based scaling is I define a certain CPU or memory on when I want to scale. So let's say I have two containers that can handle 100 requests per second. If I get 105 requests, I will need to spin up a new container to be able to handle those 5 additional requests. And that goes on up until the compute node would be full, so I cannot place no more containers on the node, and therefore a new node would be spin up so I can place additional containers. And on a first glance, in comparison to the virtual machines, that looks quite efficient, right? I can place much more containers on the same host. But also, if we think about it, it's still a bit of a coarse granular scaling in that case, right? So even though I only get 5 requests more at the initial example, I need to spin up a whole new container instance just to handle those additional 5 requests. So in a sense, we are still here more on the coarse granular level of scaling. And I think most of you are familiar with that, but this is really essential to understand that when we compare that now to our second candidate, which is serverless functions. And I want to spend a brief moment here on the terminology, because I think this is really important, and I see people often get that wrong. When we talk about serverless, what we mean is actually a way to build and run applications and services without managing infrastructure, right? So your application obviously still runs on servers, but this is done by AWS, right? So serverless doesn't mean there are no servers. There are a lot of servers, actually. And this is our colleague Dylan from the Eastern Oregon Infrastructure Delivery Team. So you don't need to manage the servers, but Dylan still has a lot of work to do to manage them under the hood. Now, serverless can be a bit more than compute or functions if we think about that. So if you're all familiar with S3 or API Gateway or Event Bridge or something like that, those are also components. For S3, you don't need to set up a storage array or something or define HDD drives, right? It's really something that you don't care. You only interact with it via an API. So therefore, when we compare containers, we cannot compare containers to serverless, but what we can compare is the actual compute model. So we can compare containers to serverless functions. Because as we will learn later also from Emily, there's also variations that you can run containers in a more of a serverless way. So therefore, our focus will be specifically on functions. And what does a function consist of? So what's the anatomy of a function? And a function usually consists out of 3 parts. So the function itself that you can see, it's quite familiar for you, just as a normal function as you would write in any of the programming languages that you are choosing. And then you have usually a context object that you can see, which has additional information about the request, things like a unique request ID. And then, most importantly, is you get that request event. So you have, depending on the service that invokes the Lambda function, you will get a different kind of structure as an input argument to your function so that you can work with that. And then you basically can define the runtime that you want to choose, like Java and so on and so forth. And then you have a certain amount of setting you can set, like CPU architecture, x86 or ARM, and a certain memory level. And the CPU and the network throughput is aligned proportionally. So usually you have an opinionated set of things that you can define, but you're not as flexible here as you would be with a container. So what happens next? Like, let's say we have written our function, and now we upload it maybe via infrastructure as code or via jar or zip file to Lambda. And now what happens next? So we take that application and we hand it over to a service. And the service, in that case AWS Lambda, now automatically runs your code. And there are no servers or clusters involved in that case, sitting there idle waiting for something to happen, and you only pay when your code is actually executed. And this allows also to scale to 0. So if there are no requests, you're not charged for any requests in that sense. So how does that work, right? It sounds a bit like magic, like scaling to 0, nothing is there, like how do I handle that? And this is done by Lambda is only executed in response to events. And an event can be a message on a queue or an API request as an endpoint. Think about, hey, I want to retrieve my orders, right? That can be seen as an event. Or maybe changes in resource state. Someone uploaded a file to S3, that can be an event, and then my function will be executed. So think about functions are always invoked. They're never sitting there idle waiting for something to happen. They're always invoked by some form of event. And if we dive a little bit deeper, we see that because we often see customers having the mental model of this is how Lambda works, right? So you have an API request or something, and let's say we have a simple function that just logs the current request ID, for example, and returns that, so nothing really fancy. But the mental model that a lot of people have is that we have an API request that goes directly to the function, and then this code is executed. But in reality, if we look under the hood, it's a bit different. Like, as containers need to run on a compute node, functions also need to be executed somewhere. And on our end, that is the Firecracker micro VM. So under the hood, it runs on bare metal EC2, where the Firecracker micro VMs are spinned up. So you can see that here. There's a whole white paper explaining all the details. But what that means is you do not have control over the actual instance where the function is placed. You cannot decide to expose that function on port 1890 on that EC2 machine. This is completely abstracted from you with the Lambda service. So you're never talking to the function, to the code directly. You're always talking to the Lambda service, which ensures that you have the certain amount of Lambda function runnings on where to place them and where to scale them. But this is really up to the service to decide. And this is a very crucial part, right? For example, you don't need to have an HTTP listener or something exposed from Lambda, right? Because always the service will invoke the function with the given payload already. So you see that here, usually the service invokes the function always with a given payload, like a JSON structure that varies based on where it comes from. If it's from API gateway, it looks different than when it comes from S3, for example. And the most important part here is to understand is because you now have that service in between, it can do a lot of things for you because it knows how many requests it gets and therefore knows how many functions to scale out. So this is an effective mental model to think about it, not directly speaking to the code, but to the service in between. And this is a very powerful concept if we think about more of event-driven architectures. When we want to read maybe also something from a queue or from a topic or from Kafka or whatever, because it's not like that you from the Lambda function would read directly from the stream. So we often get asked, do I need to put a Kafka client library or something in my Lambda function? And that is not the case. The service will pull the actual message queue or stream for you, which is called Lambda event source mapping. So whenever you configure that, the service will pull from the queue and invoke your function with the actual messages. So you see here an example for SQS. You already, as an input argument, you receive the list of messages that you're being processed. And this greatly simplifies your application code. Because if you think about containers, what you would need to build, right? You need to have a client library to pull from somewhere. You need to define scaling mechanisms. How do I scale the container if my queue depth starts increasing, for example? And all of that you don't need to care now anymore because the service knows exactly, monitors the queue depth, and spins up additional function when you cannot catch up with the actual increasing stream or offset. So this is a very powerful consideration, especially when you're building decoupled and event-driven applications. Now, from a scaling perspective also, we have seen before the long-running containers that now also on Lambda works a bit different. So we say we can scale to 0, but scaling to 0 means when the first request comes, nothing is there. So something needs to be done, essentially. So what happens if the first request comes is we need to create this execution environment, so the Firecracker micro VM, first of all. And then we need to initialize that environment. That means we need to download your code, we need to start up the JVM, we need to call static initializers or constructors, and only then we can execute that handler method that we have just seen before. And this is sometimes when you hear people talking about cold starts, or why is my Lambda function slow, for example, or why does it take some time to start? Because this is the work that needs to be done initially to be able to scale to 0 and then scale up. This can be heavily optimized in certain ways. There's Lambda snap start, for example, for Java applications. But this is something to keep in mind. There's usually a penalty on the first couple of, on the first request or concurrent requests. Because when this execution environment is warm and we have executed one, it will stay there. So the next execution will be very fast. So that means the same experience as you would have in a container. Now, an important note is that every execution environment can only handle a single request at a time. So that means if I get the third request while the first execution environment is currently processing, Lambda needs to spin up a new execution environment, have to re-initialize that again, and then do the execution. So therefore, if you have a lot of concurrent requests at the same time, you might experience multiple cold starts at that time. However, afterwards, they are warm, so they stay warm for a couple of seconds or minutes. There's no official timings that we publish there, but usually they stay warm, so you can just keep using them. So cold starts usually are only amounted to a very short period of your whole application lifecycle. The execution itself can have a maximum of 15 minutes, so this is something to keep in mind. If you have very long-running, complex calculations that you cannot further divide or something like that, or very long-running CI/CD jobs, then keep that limit in mind, because that would not work with Lambda in that case. And also, after some time of inactivity, this is the couple of minutes that I mentioned, the execution environment can be shut down afterwards. So we often get asked, now, can I put caching or something in Lambda? Yes, you can put an in-memory cache or something like that in Lambda. However, just keep in mind that at some point, the execution environment might be dismissed and you'd lose that state. So if you need that state over multiple execution environments and lifecycle, we always tell customers to externalize it into something like Elasticache or something. Now, if we have talked about now the invocation model, and I think it's very fundamental to understand the difference here. We want to summarize that in a single quote that you can all take away when thinking about, does my application fit to that invocation model? So the processing of a request in a web application or an event in an asynchronous application for a container is a unit of work, right? Among other things. So the container handles multiple requests at a time. There might be background tasks running, okay? There might be someone polling all the time, right? So usually the actual processing, so executing your business logic, is a unit of work for a container. But for the function, it is the unit of work. So therefore, the life cycle of a container is not directly dependent on a request, while for a function it is. So the request itself is the determining entity of its function's lifecycle, of the scaling, and nothing else, right? So usually you don't have long-running background jobs or something in Lambda, right? Because usually your lifetime is always triggered by a certain event, as we have seen earlier. And this is for us, from an invocation perspective, the key difference between containers and functions. Now, if we dive a bit deeper now into cost efficiency, so we've learned now both technologies, we know how they scale, what they are, what makes them different. Now let's see what that means in terms of cost. Now, functions, they provide cost efficiency in a sense because you only pay for what they've used. So you only pay for the actual execution of your function. So if your function is not receiving any traffic, then you don't need to pay for it. This is the great benefit of scaling to zero, which relates to zero cost. And that, at the same time, now also allows you to efficiently experiment globally. Because you don't have an initial infrastructure footprint, you can deploy your functions to Singapore, to the US, to Frankfurt, and if no one is using them, there is no infrastructure footprint attached to that, so you can very easily and efficiently experiment without incurring a large amount of upfront infrastructure cost. So you can test ideas and so on and so forth. And that low overhead also enables you to have an improved time to market, because you can leverage all the managed capabilities of the function itself. It allows you to get to market fast. Now let's look into containers then in that sense, right? So we said they are long running, but they also then provide us with a bit predictable pricing. So if I know that I have certain compute nodes where my containers will be put on, I know exactly, usually if I have a constant load, how much I will pay at the end of the month. And I can even then take an advantage of that by committing to things like savings plans or reserved instances to get an even cheaper price for that. And they might be even more cost efficient than functions, because, and I like to take here the analogy to car sharing or an own car, right? So if you think about functions like in a car sharing analogy, and I say, I can rent, now if I go out, I can rent 1 car, 2 cars, 3 cars, right? I can rent a car for my wife, for my son, and so on and so forth. So I'm very flexible in that sense. And this is even super efficient if I only drive the car for maybe an hour a day, a couple of times a week, for example, or only in the morning for an hour. So then car sharing is a very attractive model of doing that. And I like to think about functions from that sense, right? Also, if your car is broken down, usually the car sharing company takes care of that. And this is how you can think about also from a functional perspective. However, if I take the car sharing car and I drive it 24/7 for the whole month, that will get quite expensive, right? So therefore, having an own car, which translates now to having your own compute nodes or your Kubernetes cluster where you put your containers, can be much more cost efficient. So if you have constant load, so you know your application takes 200 requests 24/7 for the whole month, then containers will be more cost effective than Lambda, because you don't need all the flexibility that Lambda brings to you with the scaling, with the automatic patching, and therefore the containers here in that case will make, from a financial perspective, much more sense. And also, however, on the other side, you need to now factor in the operational cost. So as if your car would break, you would need to take it to the garage, right, and you need to fix it, right? And so you have some employee power, right, that you need to put into maintaining those things. So don't forget that cost factor if something breaks, or Kubernetes cluster upgrades, right? Those are things you need to take care about on the contrast. So I want to summarize here. The core difference would be, in that case, pay for an instance or compute node, and versus pay per use. And with that, I will hand it over to my colleague Emily, who will now talk about flexibility, portability, and maintenance. Thank you.
All right. Thank you so much, Max. All right, well, let's keep going. I am going to continue what we've been doing of comparing containers and serverless functions with digging into a couple of the other factors that customers are often thinking about when they're looking to evaluate some of those technology choices for the workload that they're building. So the next 3 that I want to dig into are the flexibility and portability and the management comparisons between these 2 technologies. So we've already talked a fair amount about containers flexibility. So we know that containers, you're basically running with an encapsulated version of the operating system, and so it's very flexible for what you can do with it and where you can run it on. And so with containers, you're having a ton of configuration options for the hardware that you want to run your container on. For example, things like the memory, the CPU architecture, the storage, all of those things you can really fine-tune for the workload that you need to run. For example, this can be really useful if you've got a very specific use case, maybe an AI/ML workload that you need GPUs for. In that case, containers could be a really great fit for you to be very specific about the configuration of the hardware that you want to run it on. The other thing that is very useful from a containers perspective is because you've got the same container setup, you're able to run that on-prem or maybe on your local machine as you're developing that container application. This is very useful if you want to keep the tooling consistent. Maybe you're very familiar with tools that you might use with containers or specific to Kubernetes, and you're able to apply those in the different places that you might be building. This is also useful if you're thinking about migrations. So maybe you have containerized applications that are running on-prem, and you want to just pick those up and move those to the cloud. That can be a really simple transition and one that keeps you with those familiar tools and processes that you're already building with. Now, with serverless functions, this changes a little bit. And the reason for this is because your serverless functions are going to be allocated from a shared pool of resources. And so you're going to have more simplified and fewer configuration options as you're looking to set those functions up. Now, you do have some settings, so you have ability to tweak some of the memory and CPU and temp storage, but you're not going to have access to maybe control over generations of CPU. You're just going to have the choices of x86 or ARM. So a little bit of simplification as you're pulling those functions from a shared resource pool. Now, for a lot of use cases, that's going to be sufficient for what you're trying to do. But if you are thinking about some really specialized use cases, maybe some AI/ML model training or high-performance computing, in those cases, you might want to think about containers and really specifying the hardware. Now, with the function model, this also changes what it looks like to develop your workloads and what you're looking at locally as you're looking to build. So one of the amazing things about serverless functions is just that depth of integration and native integrations that you have to the rest of AWS services in the cloud. And obviously, that's not something that you can very easily mimic on your own laptop. And so it does change what it looks like to have that local development experience. Now, there are a lot of different solutions that you have out there, whether that's a local emulation through something like the serverless application model, or you can use frameworks. So in the Java world, we have Quarkus, Micronauts, and some of those that allow you to kind of package that up and allow you to test that out in a local way. But that is something that if you're coming from maybe building on servers or building in containers, your development processes might change a little bit as you're looking to build with functions. Now, let's talk a little bit about function management. So Max has talked a little bit about all of the stuff that you are taking from a function perspective and offloading to AWS to manage and to operate for you. So things like building with high availability built in, the automatic scalability of those functions as you're having requests that are either scaling up or scaling down to 0. All of those things are things that you're no longer thinking about, things that you're no longer writing code, maintaining code to be able to do. And that puts a huge amount of the operational burden off of your plate and onto AWS to provide for you. This really shows up when we think about situations like the Log4Shell vulnerability that had a huge impact in the IT industry recently. Thinking about customers that were building on serverless functions at the time, they were able to kind of hand that problem over to the Lambda product team, who was able to resolve it for them, fix the situation, and they didn't even have to feel it or have to do any changes on their side. So super impactful if you're thinking about some of those kind of large things that you can offload to Lambda to do for you. Now, with the simplification and the offloading, there is definitely a little bit less access that you might have directly. So you're not going to be able to SSH directly into an instance, for example, like you might be able to on a container. There's a lot of logs and metrics and those type of things that are available out of the box. But maybe if you have some kind of debugging workflows or tools that you're working with that operate in servers or containers, you might need to change those or to take on a new tool as you're looking to start doing that with serverless functions. Now, in the container world, there is a lot more that you are needing to manage on your side. There are different levels of abstractions available for containers management, and we'll dig into some of those other options like Fargate and AppRunner a little bit later in the talk. But for now, let's assume that you are using ECS or EKS with EC2. And so in that case, you have all of these different things listed here that are part of the work that you need to do to manage your container. So thinking about things like the responsibility for patching images, Kubernetes version upgrades is a big one. Those are things that are going to be falling on your side as the customer that's building. But you do have that greater access to control and to be able to have that flexibility into the containers. Now, what we see a lot of customers doing, just because there is a bit more management tasks on the container side, is they're building out these platform teams that are managing that for the entire organization. And so the platform team is running the infrastructure, and they're building all of these best practices and creating a self-service model for developers in the company to be able to build their applications, focus on application development, and then come to the platform team and deploy those on the infrastructure. So that's a model that we're seeing many customers that do choose to build and standardize a lot on containers adopting. And lastly, of course, with containers, you have a broad choice of open source projects. So like those from CNCF and Kubernetes projects that you have access to be able to help you manage and do some of that work on the container side. Now, getting into portability, again, on the container side, we've talked a bit about this, where you do have a lot of portability when it comes to containers. So you're able to invoke those containers through HTTP or any protocol, and you're able to use any type of base image that you want to be able to package up and deploy that code to the container. Now, coming to serverless functions, a lot of folks will start off with a question of just a little bit of concern, maybe thinking about the portability of functions and whether it's going to be easy for them to take that function code and maybe run it somewhere else if they need to. Now, let's talk a little bit about some of the elements of building serverless functions that might be specific to Lambda and serverless functions. So the first off is that invocation model. So we talked a little bit about how when you're invoking a Lambda function, it's going to be receiving a JSON payload from the specific service that's calling it. So in this case, we've got an example with API gateways. This is the type of payload that you might receive from an API event. That's one piece of it that is specific to implementing with Lambda. Another piece is you do have a predefined format for how you're going to be packaging up and deploying that code. That could be with a zip file or with a container image. But there are some specific elements of that container image that you're going to need to be able to use that for a Lambda function. So it needs to have that runtime interface client, which is able to interact with the Lambda runtime API. And that's the piece that's going to be responsible for invoking that Lambda function and operating that code within a Lambda function. Now, with this, I believe that you really, when you're building software, you always have the opportunity to build very tightly coupled software that is tied to the way that you're implementing it today, and it makes it a little bit hard when you're looking to either extend that application or to move that business logic and run it somewhere else. But the strategies that I'm seeing customers deploy is basically taking that business logic and encapsulating that and then abstracting away the implementation details. One of the common strategies that I see people taking is hexagonal architectures, if you're familiar with that. So just taking that business logic, making sure that it's kind of isolated and available to encapsulate, and separating it out from the implementation details, whether that's the JSON payload coming from the service, or whatever it is that's specific to the way you're running with functions. This is another place where frameworks, we mentioned some of the Java frameworks, can come into play and can really help you be a bit more agnostic when you're looking to write code that you want to continue to evolve and may potentially run somewhere else eventually. So with containers and serverless functions, it really is a spectrum where on the container side, you've got a lot of flexibility, a lot of customization opportunities with the hardware you're running and all of that, but a lot more responsibility and potentially operational work that is falling on you. Whereas with serverless functions, you have much more simplicity, a little bit less control and less customization, but a lot of stuff that you're no longer needing to write code for or to maintain or to operate. Now, at AWS, we're always listening to the feedback that customers are giving us. And one of the things that we heard is that customers wanted to have more options within that spectrum. So maybe they love the way that they're building containers, love the tools and processes they're using, but want to take advantage of a little bit more of that serverless operating model. And so for that reason, we do have a number of different options in the serverless container space that I wanted to talk a little bit about. So the first one is Fargate. So if we're thinking about that stack of things that you're needing to manage within a typical container situation, with Fargate, we're taking that down. So some of the pieces of around auto-scaling or managing the underlying compute nodes, those are now offloaded to the Fargate service, and you're able to run containers in a serverless fashion. Now, we took that even a step further with AppRunner. And so with AppRunner, again, another piece, so now the networking piece. If you're not looking to set up your own VPCs or set that up for yourself, this is something that AppRunner can do for you. And at this point, you're really just managing the application and building that application, and a lot of the components of containers are offloaded to the service to run for you. Now, I did also mention that you are able to deploy function code as a container image. So this is a little bit more about that. And again, some of those specifics around the container image, it's not quite as simple as taking an existing container image that's running somewhere and just plopping that over into Lambda function. So it does need to have that runtime interface client and that interaction with the Lambda runtime API. But this is a solution for if you're very familiar with containers tooling and really want to keep that as a development process in your organization, then deploying Lambda functions with container images is a great route. So now that we have a lot of the factors that folks are comparing when they're thinking about containers, serverless functions, serverless containers, I wanted to wrap us up with a couple examples of how I'm seeing customers that are making these choices and building architectures with these different technologies. I want to think a little bit about the use case of building AI/ML applications. And let's first take a look at a customer that is using serverless functions for this purpose. So this customer is IIC. They're a research and development center out of Spain that is doing predictions for renewable energy. And they were building on-prem initially. They were finding that the on-prem system wasn't allowing them to move as fast as they wanted to. And they really wanted to be able to move very quickly and be very competitive in this very fast-paced industry that they're operating in and continue to make those predictions more and more accurate. Another thing that they wanted to do was be able to integrate with further data sources, and so continue to expand this. And also, this was a bit of a spiky workload. So sometimes there's a lot of use, sometimes there's less. And so these are the kind of the speed, the flexibility, the further extensibility that they wanted in this application. And so they opted for serverless functions to build this. And with this, they're able to generate 20 million predictions each year. And they saw a 90% reduction in the operating lift that they required for this application. Now, moving over to the container side, and where this is a great fit for AI/ML applications. Quora, who you might be familiar with if you're searching for anything online, they built a modern MLOps platform on EKS. And so with this, they have every component of the MLOps lifecycle, everything from model experimentation, model training, using some of the open source tools around model tracking, so MLflow. All of these things, and as well as launching their ML applications, are done on Kubernetes. And the cool thing about this is that they're able to run these very long-running workflows. They're able to really customize and optimize the hardware that they're running on for the ML workloads that they need to do. And lastly, they're able to employ that platform engineering model that we talked about. So the ML platform engineers are building out this platform, and the folks that want to develop and launch an application are able to come and deploy that self-service. So here's an example of where Kubernetes was an excellent choice for this customer. And lastly, as Max mentioned, this is seldom a binary decision. And so we do see lots of customers that are choosing a combination of containers and serverless functions. One of the customers based out of here in Germany is LexOffice. And they were building a SaaS application that initially was running on-prem. So they're managing their own compute, their own load balancers, databases. And they really wanted to be able to reduce their operations and move to the cloud. So they moved some of these applications over to the cloud, and then took a step further to containerize those applications and take advantage of some of the managed AWS services around containers and around load balancers and databases, and in this way significantly reduce their operations. This is also an example of many customers that we work with might have existing systems or that they need to continue to connect to on-prem, and using containers is a great way to be able to use the same development tooling both in the cloud and then with your existing systems. Now, this customer, they also had a use case where they wanted to start to build new and to decouple the monolithic application that they were running prior. And for this, they did opt to introduce some new serverless functions into the application. So this is an application that they built that whenever an invoice is generated, they're able to take that information and invoke a Lambda function that looks up the URL for that particular tenant in their SaaS application, and then find the right endpoint and invoke that endpoint. This is a very spiky workload, and so this is one that also made a lot of sense for them to use serverless functions for, in combination with the workloads that they're still running on containers. And lastly, I wanted to end on one of the customers that we're seeing build really cool things in the UK, so the Driver and Vehicle Licensing Agency. Again, doing a lot of modernizations over time from an on-prem system to a modern system in the cloud for their driver's license application processing. And the cool thing about this is that we see a combination of them running EKS for some of these long-running UI and presentation layer applications, But then sending some of those requests for customers that are looking to submit a new driver's license application to a asynchronous backend, which is using Lambda functions and some of these other serverless services to process those requests asynchronously. So this is really a combination, and to show that there's many customers that are really choosing to pull in these services where they make sense for different use cases that fit the criteria or the profile for those services, what those services are most optimized for. Now, I wanted to end with just a couple key takeaways to take with you. First off, we compared and contrasted the life cycle. So thinking about serverless functions, where the life cycle is that particular event, versus containers, which are long running and may take multiple tasks or multiple events. Also thinking about the load profile. So serverless functions are very well optimized for something that is spiky or needs to scale to 0, whereas containers can be great for if you have a long running or always on workload that you need to operate. Pricing, definitely something that is worth considering if, again, you have very consistent, very kind of stable workload that you want containers to be running for you versus serverless functions where you're only paying for use or paying when your code is running. The control side of it, so you do have a lot more kind of direct access if you're running on containers versus a little bit more of a simplified environment for serverless functions. And lastly, integrations. With serverless functions, you're able to take advantage of a lot of deep native managed integrations with other AWS services. And with containers, you also have a wonderful access to a lot of open source projects and tools to be able to help you manage containers. And with that, I will close this out by definitely recommending that you take advantage of Skill Builder, where we have a ton of great content that can help you go much deeper into containers and serverless. And thank you so much from Max and myself.